Let me formally welcome you to Surviving Survival Analysis, the second PaTaRI in this series, and we'll be talking about survival prediction with machine learning. In this, I am very grateful to the entire volunteer team. I've already named them. They've worked really hard for all of you in the TIA lab so that we can solve interesting survival prediction problems in computational pathology. So this is, as I said earlier, the second PaTaRI in the series. In the previous one, we covered essentially statistical methods for survival analysis, and in this one, we are going to talk about machine learning methods. But we will begin with a recap of what we did in the last PaTaRI, and there is going to be a quiz as well. So let's fire away. I would be handing over to Noor. If you would like to share your screen, and if you can turn your camera on, that would be nice, and begin presenting. Noor, are you able to share your screen?
Yeah, just let me share my screen first. You see my screen, Fayyaz?
Yeah.
Yeah, okay, so we will start with a quick recap of what we discussed in the last PaTaRI. So in a typical life cycle of a survival analysis project, we start with the idea, and then we of course collect data to see if that idea works. We extract features from the data, and then we fit some model for the survival analysis. We analyze the results, and then we can further look for other important patterns from the data. The survival analysis, which deals with the study of survival times and any factors that can influence the survival. The four main goals that we can achieve with survival analysis is that we can estimate the probability of an event occurring over a certain period of time. For example, in this plot A, we see the estimation of survival probability over this time. We can also estimate the hazard function, which can tell us how likely the individuals or the items are to experience an event, for example, die within certain period of time. So in this case, this plot showing the time to violent death of Roman emperors, and we can see a spike between 12 to 18 years, which shows there's a higher hazard of dying between this time of the reign. And similarly, starting initially, the hazard is higher, but in between 4 to 10 years, the death ratio is low as compared to the other years. Another goal we can use this survival analysis for is we can compare two groups if they are significantly different from each other. In this case, a group that received chemotherapy before their surgery, and another group which received chemotherapy after surgery. And then we can visually see the curves, and we can quantify them using some statistical test to see if they are significantly different. We can also assess the effect of different features, for example, race, age, etc., on the survival with these hazard ratios we will be discussing later on. A typical survival model, let's say Kaplan-Meier or any proportional hazard model, it takes in these three inputs. The first is the time when the event occurred or when the individual was censored, and if the event has occurred or not, and any features that we can obtain for the individuals. and the output would be, of course, the survival to certain time. So we'll be denoting the time to event by Ti. So for each individual, we have time of the event. Then we will have the Di if the event has occurred. We will put a 1 in the table if the event hasn't occurred, which means the individual is censored. In that case, we will put a 0, and then we will have, of course, the features. The difficulty we discussed last time as well is that this survival data is usually censored, which means that for some individual over the study period, the event might not occur. For example, in this case, the individual B, till the end of the study, that is 12 weeks, the event hasn't shown for this individual. So this is censored, and it is right censored because the event can occur after this study time, or some of the individual might withdraw or they are lost to follow up. So those will be censored because we don't know the exact time of the event. There are two other variants of the censoring, but the right censoring is the most frequent one. There's left censoring when we don't know when the individual entering the study already had that event occurred. And sometimes we know that the event is in between two intervals, but we are not exactly sure what that exact point is. So this interval censoring. The first method that we discussed to estimate this function is the non-parametric method, that is the Kaplan-Meier estimator. And what it does is it estimates the survival probability over time. And how it does it, it takes the product of the survival at each time, let's say Ti, and up to time T, we take the product of these conditional probabilities, where the Di is the individual which have experienced the event at this time Ti, and the Ni would be the number of individual at risk at time T, at time I, which means how many individuals have survived till this time, and this will give us the survival function, which we can visualize with the Kaplan-Meier curves. And this tick bar will represent the censoring event, and the drop in the curve means there is an event occurring there. So on the left we have this survival function. In this plot we see the curves for males and females surviving over the years. We can see these two groups. The curves can tell us this. The females have survived more than males in this case. And of course, the survival time is going down when we are going up about the 40-year mark. On the right, there's another important function that is called hazard function, which is the instantaneous death rate. For example, if an individual has survived up to time T, what's the probability that this individual will die or the item will fail in the very next instance? So this rate is called the hazard function, and this hazard function we will discuss later, that we can use these hazard function to compare the hazard between two groups, which we will term as the hazard ratio, which can tell us different things. These two functions, the survival function and the hazard function, they are related by this equation. So if you know the survival function, if you have the survival function, you take the derivative, log derivative of the inverse survival function, and we will get the hazard function. And in the reverse, if you integrate the hazard function, you have from 0 to up to certain time, and take the exponential, you will get back your survival function. This is an example of the Kaplan-Meier curve. We have the time at different intervals. If there is an event occurring, we are putting 1 for the sensor data as 0, and the number of individuals that have survived till each time. Using our estimator, we are calculating these probabilities, and which is of course at any time the probability is a product of all the probabilities before this time, and we can visualize with the curves. We can use these curves to visually see if there is any separation between these groups, let's say chemo before and chemo after. So we again use the estimator to get the probabilities for each group. This is the first group, and then this is the second group. We plot them visually, but to quantitatively see if these groups are significantly different, we will perform some tests which can give us a p-value, and we can set a threshold. If the p-value is below, let's say 0.05, then we can confirm that indeed these groups are statistically different in terms of their survival times. And the most frequently used test for this is the log-rank test, which compares the survival probabilities of the independent groups. And we are actually trying to reject the null hypothesis that there is no difference between the survival times for the two groups. And by rejecting this null hypothesis, we will be accepting our alternative hypothesis that there is indeed a difference between the two groups. For this, the chi-square test is used. Other tests like Wilcoxon or Teroni-Vary, Peto, Flemington, Harrington, also reported in the literature. So what this test does is you calculate the test statistic and look up the critical value table for a certain p-value. And if your test statistics is above the critical value at that level of significance, then you can reject the null hypothesis and accept your alternative hypothesis. So for example, for this data, the p-value is less than 0.5 when we look up in the critical value table. The test statistic 3.841, or computed test statistic is 6.1, which is greater than this p-value. So we can reject the null hypothesis that there is no difference, and then accept our alternative hypothesis that there is indeed a difference between the survival time of these two groups. Now, when we are comparing two groups, we also need to assess the effect of different other features like the age of the patient, the size of the tumor, or any other factor like if smoking can affect the survival. So when we take those features or covariates into account, then it becomes a multivariate analysis. And of course, it's impossible to take everything under control, but whatever features we can, we should be assessing them in the survival analysis to get a good estimate of the survival probability. I think Amina will be discussing these multivariate analysis in detail. Amina will be sharing her screen if there's no question this time.
While Amina is setting up, if they thank you, Noor. Are there any questions for Noor? So essentially what Noor has presented is a way in which you can analyze different groups and how you can plot those survival curves.
I had one question on the table for survival. I think it's gone now.
Amina, can you do it?
Which table is that?
Can you share the screen, Noor?
So you can't see my screen?
No.
Can you see it now?
Yeah.
Yes, it was on the next slide probably. Yeah, I mean, I was looking at number at risk and number of deaths. So you have, if there is one death, then how can the number of at risk still remain the same? I was just.
Repeat your question, Shan.
So these two columns, number at risk and number of deaths.
This one and this one.
Is equal to 8. You have number at risk is equal to 10 still, but you have number of deaths is equal to 1.
Yeah. So this is the starting point. Yeah. At the start of this follow-up, we have 10 individuals surviving. Okay. then one of them dies and one of them is censored. So at the next interval, when we are calculating this statistic, we have only 8 individuals left because one has died, one is censored.
Okay, it's the next. Okay.
Yeah.
Thanks.
Thank you, Shan. So yeah, you can write a recursive function as Noor has done to calculate these. Amina, I think it's your turn to share your screen. And if there are any questions, please feel free to ask. The goal is essentially to learn from each other and be able to apply these concepts in practice. So fire away, Amina.
Can you see the screen?
Yeah.
Hello, everyone. So I'll be presenting the second part of this recap session.
Please, it's yeah, now it is. Thank you.
So when we talk about survival analysis, we are typically interested in two things. One of them is definitely the modeling of the survival function, or equivalently the hazard function. For example, like the one you can see on the top right of the screen. And the second goal that we are interested in is to evaluate the effect of a variable, which is commonly known as covariate in statistics literature, on survival. It can be gender, age, drug, or something your machine learning model produced. So we are interested in seeing whether those particular variables have an effect on survival or not. And Noor has just described how we can use Kaplan-Meier modeling for this purpose. If we have a categorical variable, we may divide our data into groups based on the categories of that variable, and then we may apply log-rank tests to see whether there is a statistically significant difference between the groups or not. And if there is, we conclude that there is an effect of that variable on the survivors. However, what if we want to analyze the effect of some non-categorical variable, for example, age, using Kaplan-Meier modeling? Now, the naive solution would be to discretize this variable based on some threshold and then perform a similar analysis. So perhaps if you have age, you will try to categorize it into, let's say, young and old based on some threshold value. Now, there are two problems here. The first one is, how do we come up with a proper threshold? Using some sort of discovery cohort. What if that discovery cohort isn't representative of the whole population? The second problem is, let's suppose we come up with a threshold of, say, 60 years to categorize people into young and old. What we are essentially saying is that a person who is 59 years old is supposed to have characteristics more similar to someone who is 2 years old as compared to a 61-year-old. So there are problems like this when we forcefully try to categorize variables that are not categorical in nature. So therefore, we need methods that can help us evaluate the effects of variables that are continuous or non-categorical in nature. So Kaplan-Meier modeling, it cannot model the effect of continuous features, and as Noor has already mentioned, multivariable analysis is hard to perform there. So for that purpose, we have several semi-parametric and parametric models in the literature. There is a long list of those methods, but we'll be discussing the one you'll most frequently come across in the literature, and that is the Cox proportional hazards model. Now, Cox proportional hazards model assumes that the hazard of an individual can be given by this mathematical formulation here. That is, it is a product of a baseline hazard with an exponential of a linear combination of some features represented as x1, x2, so on to xn. These parameters beta are estimated while we are fitting the model. This model is known as it comes under the category of semi-parametric models, because this half, that is the baseline hazard, we don't have any excuse me, assumptions about the shape of this baseline hazard. Now, before using this Cox proportional hazards model for modeling survival for your data, there is one thing that you should be very careful about, and that is the proportional hazards assumption. This model is based on the assumption that the ratio of hazards of two individuals remains constant over time. So what we are saying is that if person A is twice as likely to die as person B at a given time instance, let's say T1, person A would be twice as likely to die as person B at some other time instance T2 as well. That is, the ratio of hazards remains constant throughout time. If it's not being satisfied, this assumption is not being satisfied, then you should not be using Cox proportional hazards model. The effect of a feature in this Cox proportional hazards model is evaluated using something known as a hazard ratio, and which I'll be talking about in a couple of slides. So the last thing that we'll be covering in this recap session is the evaluation that we perform in survival analysis studies. Again, like I said, we're interested in two things. One of them is to analyze the effect of a covariate, and the other thing is to model survival. So if we have a particular feature and we want to see how it affects survival, two of the things that we can use are p-values and hazard ratios. And if we want to evaluate the performance of our survival model, that is, how good is our model at predicting survival, then we may use concordance indices, Brier scores, and several other evaluation metrics. Please note that this list is by no means exhaustive. There are tens of other measures for both of these for both of these types of evaluation in the literature, but in the interest of time, we have chosen only the most frequently used ones for this presentation. All right, so p-values, to put in layman's terms, it is how probable is it to observe a particular difference, how probable is it that the difference you're observing happened by chance? So it is a measure of significance, and we typically like these values to be small. So just to cite the example that Noor has already presented, for example, here on the right, you can see that for these two groups of chemo before and chemo after, we got a p-value of 0.0085 after the log-rank test. So what we are essentially saying is that there is a probability of 0.85% that this difference that we are observing happened by chance. Now, we might be able to identify if two groups are statistically significant difference between two groups. However, using p-values alone, we cannot quantify the effect of the variable using which we have performed stratification. We need something else for that to see what is the effect of the particular variable that we have used to group into these two groups. So something known as hazard ratios can be used for that. As the name suggests, it is the relative risk of two groups. For example, we want to see whether administering a drug to a group has an effect on survival or not. So what we'll do is we'll take a ratio of the hazards at time t for the group that was given the drug with the group that was not given the drug or was in the placebo group. We will get a number for this ratio, and how do we interpret it? If the number is greater than 1, it means the drug increases the hazard, or in other words, the drug has a decreasing effect on survival. So probably you don't want to administer that drug if increasing survival is what you're looking for. A hazard ratio of 1 or close to 1 means there is no significant effect of the drug on survival. And a hazard ratio of less than 1 would mean that the drug has a decreasing effect on hazard and hence has an increasing effect on the survival of an individual, and perhaps it would give us something in support of that drug, that it is increasing the survival of a particular individual. Okay, coming to the last part, that is the model performance evaluation in survival prediction models. So what if we want to quantify how good is our survival prediction model? One of the measures that is most frequently used is Harrell's concordance index. And as the name suggests, it measures the concordance between the predicted values by your model with the actual survivals of individuals. So it determines if the ordering of predicted survivals is the same as that of the actual survivals of individuals. So the values, you typically get a value between 0 and 1. Theoretically, a value close to 0.5 would mean a random performance. However, a perfect survival model would give you a C index of 1.0. There has been a lot of study in literature, and it has been found that concordance indices can be overly optimistic in case of high amounts of censoring. So if you have a large number of censored examples, you may not want to use concordance indices. Now, the problem with concordance indices is that they are giving you a quantification of how good your model is at ranking. But if you're interested in finding the difference between the predicted and the actual survivals, or something that you could use to quantify accuracy, you might want to use something called Brier score. It is the square distance between the observed survival status and the survival probability as predicted by your model. So this is basically an error measure, and you get a value between 0 and 1. You get a 0 for if your survival model is perfect. You will get a value close to 0.25 in case you have a random predictor, and therefore it should be less than 0.25 for a model that is able to predict survival to some extent. Again, for Brier scores, it has been shown in literature that it is not suitable when event prevalence is low. So that was a brief summary of some performance metrics that we had covered in detail in the last PaTaRI session. If there are any questions or comments, you're more than welcome to go ahead. If not, we have a quiz coming up for you.
So by asking questions, you can delay us asking you questions.
Yeah, I have a question, if that's okay.
Yes, go ahead, please.
Thanks, Amina. Can you go to the previous slide, please? Yeah, I fail to understand what the comparable pair means here.
Okay, a good question. So we are taking pairs of examples in which one of the examples will have a lower survival time as compared to the other. However, a comparable pair, that is, we will allow only those pairs for which the individual with the lower survival time has already observed the event. If not, that pair won't be comparable. Does that answer your question?
Yes, it does. Thank you.
Welcome.
Yeah, I think it's going to be Adam with the quiz if there are no follow-up questions. I just have a comment, Amina, if you can go back to the previous slide, sorry. So not suitable when event prevalence is low, and saying that in case of high censoring is actually the exact same.
Yep.
Yeah.
Yes, there.
So
but I didn't want to repeat the same sentence on the slide, so yeah.
Okay. It means the same thing though.
Yes.
Great, so I haven't got any slides to actually share, but can everyone hear me, sorry?
Yes.
Perfect. So I have sent an attachment with a link to a Google Forms, which we've got a quiz on. So if everyone wants to click on that attachment, we can and just have a go at the quiz, and I'll give you 5 or 6 minutes or whatnot, and then we'll go over the answers. But thank you very much.
So please go ahead and attempt the quiz. It's you'll also get answers while after you submitted your quiz. So it would be a good test or self-evaluation of different concepts that we've tried to cover.
Yeah, and I'll quickly go over some answers at the end if there's any that a lot of people got wrong, or if anyone's got any questions.
And if I may request everyone who has attempted the quiz to please go ahead and like the quiz message by Adam in the PaTaRI chat session, so we know how many people are actually attempting it here. Just like this one. So please feel free to attempt the quiz. It's really simple, or not.
I noticed that one of the questions doesn't have an I don't know option. So there's one question you're not allowed to not know the answer for.
Yeah, you've got to answer that one, I'm afraid.
So I can only see 5 people. Come on, TAA. We need more volunteers for the quiz. So.
It's a nice and easy quiz, I promise.
And it's anonymous, so everyone can pretend to be Nasir.
So we're starting to get quite a few responses in now, so I'll give it another minute and then I'll go through the answers.
There are some tough ones in there, Adam.
Oh dear.
Those are good, but it's really stimulating. Nice.
Good. Okay then. Well, it's been 6 minutes now, so I'll start going over the answers. I'll just share my screen.
Go ahead.
Perfect. Can everyone see my screen okay?
Yep.
So we've had 10 responses through now. So, and I'll just quickly work my way through some of these questions, some of the answers, even to the ones that people have got wrong. And if anyone's got any questions at any point, just stop me and we'll go through it. So, the majority of people have got this one right here, but the hazard function gives the instantaneous potential per unit time for the event to occur, given that the individual has survived this far. So at the end of each question, I have given an answer and generally some feedback if you didn't get it right. But that's pretty much the definition of the hazard function. So at each point, if the individual has survived this point, the hazard function is worked out, is calculated to be the potential that it then have an event with respect to all the patients that are left in the study. So it's the instantaneous potential at that time. I hope that makes sense. So there was a slide that Noor showed, and it shows that actually the hazard function and the survival function are related to each other. So I can't remember the exact formula, but the hazard function is, I think, the negative derivative with respect to time of the natural logarithm of the survival function. So they are related to each other, but it's not necessarily the most simple of relationships. So here is potentially a little bit of a trick question. The hazard function is a curve that decreases from a point at t equals 0 of being 1 to a point at t equals infinity equals 0. So that's so the people who've gone through there, that's actually the wrong way around. So that's the survival function. The survival function starts and everyone is alive at t equals 0 in theory. So your survival probability is 1. However, at the end at t equals infinity, the survival no one is in theory is left alive. So the survival function is 0 at that point. The hazard function takes, as I already said, it's got a relationship to the survival function that isn't necessarily that straightforward, but you will never get a point where the hazard at t equals 1 is 0, because that way every single person would well have an event straight away.
Adam, I have the same thoughts for you as some of my students would have for me if I put this question in, because it's tricky, but it's good. It really made me think.
So I think it's just 2 people here that's got this one wrong. The construction of KM survival curves and performing a log-rank test to compare 2 groups is an example of multivariate analysis. So I think Amina mentioned that a bit more towards the end, but this is actually a univariate analysis, so it can only account for 1 feature. So you can't use multiple different features. So that's why we look at using Cox proportional hazard models instead, and that way we can incorporate multiple features into our equation. So again, this one, so censored data are not normally visualized on a KM curve. That maybe isn't the best worded question, but generally when you do a survival curve, you put a cross on the curve if people are censored at that stage. So it'd be nice to have an image really here, but yes, it's normally visualized by a cross on the curve, but sometimes there's dots. So it looks like about half the people didn't know the answer to this question. We didn't go over this in the actual in the slides. I know we did last time, but I suppose that's probably why most people haven't known the answer to this one. But that's exactly correct. We can compare the log-rank test statistic to a chi-square distribution, and that's how we find out significance between the curves. So the survival probability on a KM curve is re-estimated each time an event occurs. So this is what Noor talked about for a little bit, and it's because the data is censored, then you can't use every single participant at each time point. So you can only use a participant that's been censored up until the point at which they're censored, and therefore the survival probability is actually recalculated at every single time point. And that's the way, and it's the form. I can't quite remember the formula off the top of my head, but Noor displayed it on his slides. So this is a subtle, maybe a bit of a pedantic answer here. When only two groups are being compared, the log-rank test is testing the null hypothesis that the distributions are different. So the null hypothesis for a log-rank test is always that the null hypotheses are identical. So it's the devil's advocate is the alternative hypothesis. So your alternative hypothesis would be that they're different. So go on to round three. So I think most people have got this one right, and that's simply because the Cox-PH and hazard model is a semi-parametric model. So you don't actually have to specify the functional form of the curve. It's including the baseline. It's the baseline hazard. Instead, you just specify an exponential term, which includes a linear sum of the features. If it was a fully parametric model instead, such as fully parametric proportional hazard models that we haven't actually covered today, but we did cover last time, then you specify the functional form of the survival curve. So it might be e to the minus lambda t, or some form of curve like that. So yeah, again with this one, most people got this one right. The Cox-PH model relies on this proportionality assumption. So this is what Amina showed in some slides, and it shows that the ratio of the hazards for any two individuals has got to be constant over time. So that's the whole assumption of proportional hazards. So again, most people got this one right. A Cox-PH model, the baseline hazard is a function of time. So if you might remember from, I think it was Amina's slides that showed the Cox model, and it's that h is the hazard is equal to h naught, the baseline hazard, times by an exponential term, which was e to the minus, and then, as I say, a linear sum of the curve, the features times by a coefficient. So that's the definition of a Cox model. So the actual terms that you specify in terms of the features don't have any time dependency. It's only the baseline hazard. I think. Okay, so number 6. That was maybe a tricky p-value question here. It's I think this is something that people quite often get wrong when they look at statistical analyses, and they assume that p-values indicate like a smaller p-value is much better. That a p-value of 0.001 is better than a p-value of 0.01, which isn't necessarily true. You might remember that we did quite a long section last time on p-values being a discrete random variable, and just the p-value you get only gives significance, it doesn't give effect size. So if you get a p-value less than or equal to 0.05, it's significant. It doesn't necessarily mean that a smaller p-value is more significant. You get how big the effect is from a variable, from something like an effect size, which might be a hazard ratio, which we get in a survival analysis. Looks like most people got that one right. And finally, generally a good model is thought to have a Brier score greater than 0.75. So that was actually the last slide that Amina presented, and so I think we're pretty well split there. And a Brier score, if you remember, is the difference between the rank and survival probability, not the rank, sorry, the status and survival probability squared. So if you have a model that has a purely random probability of 0.5, then and your rank is and your status is 1, so you've survived, then you automatically get a Brier score of 0.25. So a good model is considered to have a Brier score less than 0.25. So it's actually 1 minus what we've got there. So the answer was false, but I appreciate that's probably a little bit tricky. Great. So has anyone got any questions now that I've finished going over the quiz?
So everyone also got the answers to their quiz, right? And while they were attempting it. So that would be helpful. If you do any follow-up or get tempted, feel free to do that. Thank you, Adam, for organizing that. And let's move to Wenqi, who would be to quickly about to her coding. How do we do KM curves and log-rank tests in Python? Please go ahead, Wenqi. I can't hear you for some reason.
Okay, and what about now? Can you hear me?
You know.
Okay.
Yes.
Yeah, hello. So I'm gonna give a quick recap of this notebook that I showed in the last PaTaRI. And this notebook, it uses this simulated data set, which has 1,000 subjects, and each subject has 10 features, and also the time that this event happens, and also if the event happens or not. And these 10 features, and we name it as X1 to X10. Okay, so the first one that I showed you in this notebook is how to use Kaplan-Meier curve to try to estimate this and its survival function. So here we call this Kaplan-Meier fit, and so here we call this Kaplan-Meier filter function from this lifeline package, and fit this model on this time and also this event columns of this dataset. And then we can plot this figure here. So you can see when the time increase, this survival probability should decrease. And you can also get a summary about this life table. So something like the number of subjects censored and maybe objected and maybe removed and also observed, and also the number of subjects at risk at each time. So you can see the time of subjects who are at risk and also censored at each time point. And you can also get this survival probability by calling this survival function method. And you can also call this confidence interval method to get this confidence interval of this survival probability at each time point. Okay, and I will skip this part. Okay, so this second one that we discussed is about how to use Nielsen-Allen curve to visualize this cumulative hazard. So here we call this function, which is called Nielsen-Allen filter, from this lifeline package, and we fit it on this time and also this event columns, and then we can get this plot. You can see that when the time increase, this cumulative hazard should increase. And you can also get this specific value at each time point by calling this predict method. Okay, and the third one, it is about how to use log-rank test to compare this survival distribution between two groups. So here we take X8 feature as Y. So as this feature that we want to say. So here we can assume this feature, it is the years of smoking. So here we take the mean value of this feature as this cutoff value and divide the whole data set into two parts. And therefore this whole data set it will be divided into two parts, which are and one group should have longer smoking years and another group should have shorter years. So then we should fit this Kaplan-Meier curve on both groups, and then we can plot this curve here. So then we need to use this log-rank test method from this lifeline package to calculate this p-value based on these two curves. And so here you can see we get p-value which is much smaller than 0.001, which means this feature, which is x8, it is, and so you can say this feature it is, and so you can say this feature it can differentiate this survival distribution between these two groups significantly. Okay. Okay, so now we only consider one feature, but what about we have more than one features? So here we show you how to use Cox. So here we show you how to use Cox proportional hazard model to do this multivariate Cox regression analysis. Okay, so here we use all the 10 features and also this time and the event information. And we fit this Cox proportional hazard model on this dataset, then we can get this table here. So in this table, you can get some information like for each feature, you can know this regress coefficient, and you can also get this hazard ratio. And if this hazard ratio is higher than 1, it means increase of this feature should increase the risk of death. And you can also get this confidence interval of this regress coefficient, and also get this confidence interval of this hazard ratio. And you can also get this p-value of this specific feature here. And we can also get this concordance index, which is 0.88. And there is some other way to calculate concordance index. So you can call this concordance index method from this lifeline package, and then you can get, and then we can get the same value, which is 0.88, comparing with this one. Yeah, okay, and you can also plot this regress coefficient using this plot method. So from this figure, you can see x8. It has this highest regress coefficient, and also it is higher than 0, which means this feature it has a larger influence on the risk of death comparing with other features. Yeah, so I will skip this part. Yeah, okay. And after we get this fitted Cox model, we should be able to use it to generate a new feature, which is called partial hazard. So here I show you how to do that. So first we need to divide the whole data set into training and test. And then we fit this Cox proportional hazard model on this training data set. Yeah, and after we get this fitted model, we can call this predict partial hazard method on these two data sets to generate this partial hazard on both data sets. And here we take this hazard partial. So here we take this partial hazard as a new feature for further analysis. So here we take the mean value of this training risk score as this cutoff value and divide this training data set into two groups. And then we fit this Kaplan-Meier curve on these two groups, and use this log-rank test to calculate this p-value on this discovery cohort. So here we get a very small p-value here, as you can see here. Yeah, and then we need to say its performance on this test data sets. So here we use the same cutoff value that we get from this training data set and divide this test set into two parts. Then we can again fit this Kaplan-Meier curve on these two groups and calculate this p-value here. So here we can say we can still get one statistically, and so we can still get one statistically significant p-value here. And when you call this concordance index to calculate this C index here, so we can get 0.88 C index on this validation cohort, which means our new feature, it is shown significant on both discovery and also validation cohort. Yes, and that's it. And so I wonder, is there any questions?
Thank you, Wenqi. So essentially, whatever we have discussed in terms of theory, you can very simply apply in Python, and Wenqi has produced a notebook that you can use as a reference. Thank you. Are there any questions? If there are no questions there, we'll move on to, I think it's Adam.
Yep, that's right. Share my screen now.
Wenqi, can I request you to put the link to that notebook in the chat so everyone can use that as notes?
Yes.
Perfect. So given that we've just talked quite a lot of detail and when she's just gone for a notebook about the Cox proportional hazards model, why should we go and use machine learning instead is probably quite a good question. So the Cox proportional hazard model has quite a few assumptions. And for a starter, it relies on this proportional hazards assumption, which we talked about quite a lot. And in the case of your data, this is not necessarily always going to be true. So that's definitely one limitation. Also, we've also got this problem with handling ties. It's not done very efficiently in the Cox-PH model. I'm not going into too much detail about this, but it is quite computationally intensive in the way it's done. The third problem is that we haven't got a time component that's explicitly modelled by in terms of our features. So if you see our Cox-PH hazard function, we've got a baseline hazard and we've got this exponential term, which is this linear combination of our features. There's not necessarily a time dependency involved with our features here, which is not always useful. And finally, we always do it in terms of a linear model, and that's not always good. It's a big assumption to assume that our models always be linear, and maybe we should use nonlinear models instead. So I'm just going to quickly present survival prediction as a machine learning problem before we go on to discuss different survival models, such as support vector machines, such as random forests, and a few other different models as well. So if we've got a data set D, then, sorry, was someone got a comment then?
No, please proceed.
So if we've got a data set D and we have n different subjects, then there's a triplet of information for each subject. We've got a feature vector, X, and we've got a time, a survival time or a censoring time, and we've got delta, which is where an event occurred. So for a delta equals 0, there was no event, that patient is censored. If delta equals 1, there was an event. And what we want to do is we want to make a model. So we want to make a model f of xi, which minimises the loss function to penalise missed survival errors. And we do this using a set of comparable cases to train the model. So I've got this function here, sorry, this set P, and what this shows is that we've got, for subjects I and J who are being compared, if the survival time of I is greater than J, then J must have had an event. So otherwise we can't compare them. So if the survival time of I was greater than J and J was censored, you can't compare an event that was, you can't compare a survival time that's greater than someone else's survival time which has been censored before then. And then what we want to do is, given that we know the survival time of I is greater than the survival time of J, we want to be able to compare the cases and train the model to give a result that the f of xi is greater than f of xj, so our prediction. So I'm going to go into more detail about survival SVMs, and these are an extension of the standard support vector machine, but to right censored time to event data. And before I go into much detail about that, I'm going to quickly recap about what we know already about standard SVMs. And we know that they can be used in a linear or a non-linear fashion. So here we've got an example of a soft margin linear SVM. And what you see here is we've got this optimal hyperplane given by this line f of x, which is w transform times x plus b. And in this situation, we have f of x equals 0. And then we have these two margins. We have a margin given here that is given by a support vector in both situations, and this margin might be f of x equals 1. This margin might be f of x equals -1. And what this hyperplane does is it separates our data into two distinct regions for each class. So here we've got the red class, which might have a class of y equals 1, and the green class might be y equals -1. But with soft margin linear SVMs, you can have some violations to this constraint, which you can see here. So in terms of the evaluation, we've got this objective function here, which is we've consists of a regularization term and a loss term. So there's also this coefficient C, which is our regularization coefficient. For high values of C, then we give more weighting to the loss and less weighting to the regularization term. For low values of C, there's more weighting to this regularization term. And this regularization term really, it ensures that we get this maximal margin. So the margin here is shown by this purple line, and I should have a laser pointer really, that might be easier. Is shown by this purple line, and also this regularization term also ensures that we have ensures that the weights are kept small, because we want our weights to be small, because if they were big, then any small change in the input might result in a large change in the output, which would be undesirable. In terms of our loss function, it's simply the hinge loss, so it's the maximum argument between 0 and 1 minus y of I times f of xi. So if we look at these examples over here, if we think of all these red cases that are above the line here, where f of x is equal to 1, if we look at this particular one here at the support vector, then this here is it's got a class of y equals +1, f of xi is equal to 1, 1 minus 1 times 1 is 1, so it's equal to 0, sorry. So there's no contribution from this point or any of these points to the loss function. However, for the subjects that violate this constraint, so such as this participant over here, then f of x is going to be less than 0, and we know that y is equal to 1. So y of 1, you get a negative number here, so which results in a positive contribution here, and therefore we contribute to the loss function. I'm not going to go into any detail really about nonlinear SVMs, but I'm sure everyone already knows how they work. They work by taking a problem that isn't linearly separable, transform it into a higher dimension, or into a different feature space in which it's linearly separable. And it does this via the kernel trick and by kernel functions. And that's exactly the same for survival SVMs as well. But survival SVMs typically treat the task in two different ways: as a ranking problem, but also as a regression problem. So as a ranking problem, we're trying to get the order in which the events occurred, but not necessarily when the events occurred. So whereas a regression problem tells us the time at which an event occurred. The representation of this is exactly the same, and so is the evaluation. So we're still getting a hyperplane, and we've still got two terms, a regularization term and a loss term. If we think about just ranking first, then we've got this. We've got the exact same objective function, same regularization term. The loss function is slightly different now, and instead of having a hinge loss, we've now got a hinge square loss. And we're again using participants that pairs of subjects that satisfy this formula. And so here we've got I and j, and if the survival time of I is greater than the survival time of j, then j must have had an event, and we've already discussed why that's important. So in terms of this loss, then a larger wx implies that x should be ranked higher, and therefore results in a lower loss. So given that we know y of I is greater than y of j, then the prediction for w transpose times x of I, if that's greater than the prediction for w transpose of xj, then it means that the contribution to the loss will be less. Whereas if it's wrong, then it's 1 minus that, and you get a squared term as well. And you get a bigger contribution to the loss, sorry. So in terms of our regression survival SVMs, it's again a very similar formulation. We've got the same objective function, same regularization function. Instead, our loss term is just slightly different. So this time, it treats the problem as an ordinary least squares problem, where the loss is just based on the sum of squared residuals. So here we've got the sum of squares, and here is just our residual term. And that obviously accounts for censoring. So if there's no censoring, it's just y minus f of x. If there is censoring, then you have to take the maximum value between 0 and y minus f of x. And that's because for patients that don't experience an event, the survival you only get an error contribution if the survival is predicted to be less than the time of censoring. If it's predicted to be higher than the time of censoring, we don't know what the error is, so we have to have a 0 loss. So just to quickly compare traditional versus survival SVMs, what we've seen is that both of them can be done in a linear and non-linear fashion. I know I haven't really gone into much detail about non-linear, but I'm sure everyone's already aware of how they work. And we can treat, in traditional SVMs, we can treat it as a classification or regression problem, but in survival SVMs, it's normally treated as a ranking or regression problem. Our representation is exactly the same. We're still trying to fit a hyperplane, and our evaluation has got this same regularization term and loss term. The loss function is just slightly different when we use a traditional SVM to a survival SVM. So traditional SVM, you can see that we're using a hinge loss, whereas for survival SVM, you can see that we're using two different types of loss here. So I've just added together the different loss terms here and added a coefficient in front, R, which tells us whether to use regression or whether to use ranking. So over here, R equals 0, we treat it as a regression problem. R equals 1, we treat it as a ranking problem. So here for the ranking, we have a hinge square loss, whereas for here we have the sum of square residuals for regression. Perfect. So I'm going to pass you on to David now, who's going to talk about another regularized model, which is called Cox-Net, and it's based on the maximum likelihood estimation. In the meantime, if anyone's got any questions, please feel free to ask.
Well, is it Rob talk now? Is it Rob?
No, I think it's you, David.
Okay, sorry.
In the meanwhile, so essentially, if you can simulate loss function, you can use the machine learning model together with that. So you can click on present right next to the button on the right. Present.
I'm sorry. So I'm going to talk about the basic logic underlying Cox-Net. So Cox-Net and GLM-Net, GLM stands for General Linear Model, are very intensively used R packages. I haven't used them at all, but what I've read is that there are implementations also in Python and MATLAB, which people don't like so much. So for more information about this, refer you to Google this Cox-Net fit Cox model with various regularization forms, and I'm particularly going to talk about regularization and also this GLM-Net vignette. You know, they have vignettes in R. They're vignettes which describe how programs work. So first of all, we all know we've talked. I mean, Adam talked about regularization, which is putting a penalty on the weights, which are also called parameters or coefficients, when these weights get too big. So you just take a constant lambda, which depends on which you choose depending on the kind of data you have available, and this gives you a differentiable. The first L2 penalty for large weights gives you a differentiable result, and so that's nice for gradient descent, but it often leaves lots of small values of W, small weights around, which are not really relevant. An L1 penalty tends to clear away the small weights, the irrelevant ones. And now I want you to feel the difference, which is feel it in your gut rather than in your head by doing mathematics. So I've made this slide with two cyclists racing for an ice cream at the bottom, and they're racing on poorly maintained bikes, so that this lower cyclist probably gets exhausted about here and has to get off his bike and drag it towards the ice cream. In the meantime, the one on the faster slope has gobbled it up. So I can remember it this way, that why the L1 penalty for large W gobbles up the W, the smaller W's. So in the Cox proportional hazard model, we have N patients with P features. So they could be things like age, weight, or cigarettes per day. Now the killer is this genomic data, so that can be huge, tens of thousands of different features, and that makes regression very difficult when there's huge numbers of features. In any case, so it's very important to use something like the Lasso method, which is what the L1 method with the is called, and to remove the large number of features that are independent, that are really irrelevant to the problem. And we sum up we have a usual data matrix that you get in statistics, which is the N by P data matrix. And you first have to do the standard precaution of transforming the scale of the columns so that the mean is 0 and the standard deviation is 1. Then I've got this quote from a social science journal, and it says, "For survival chances, it is much more dangerous to be poorly educated if you're black." So this is an example of a multiplicative effect. So social scientists have found that many survival statistics are multiplicative. And if you smoke, as well as being poorly educated and black, then you have to, you multiply the hazard by a factor. You make it that much worse by a multiplicative factor. If you formulate this this finding in a mathematical way, then you get this formula with the exponential. Here you just use dot product of a row vector with a column vector, and our task is to estimate beta, which is this unknown vector. So how do we estimate it? Well, the formula, which I remind you of for the Cox proportional model, here the index R represents a certain particular patient. And so for that particular patient, the hazard is, the baseline hazard H0, multiplied by this exponential term where XR is the rth row of this data matrix representing the quantified features of the rth of patient number R. And just notation, at time TR, R dies, and we represent R, capital R of R is just a notation for the set of survivors just before time TR. So what is the probability of R being the person who dies at time TR? Well, the only thing you have to go by is this exponential term, and in order to make it into a probability, we have to divide by all the other candidates who might possibly die at that time. So it's only the survivors who might die. So you have to add all those together to make this into a probability. And now the various deaths during the study are independent of each other, hopefully. So in order, when you have independent events in probability, you have to multiply the probabilities, and then we get this likelihood, which is the product of the PRs which occur further back. And you can only multiply over the when the patient has actually died. So D is the set of recorded deaths, and you have to multiply those probabilities together. Now, when you multiply probabilities together, they get extremely small, and it's advantageous to take the logarithm. So we take, this is the log likelihood, it's called. And now the standard method in statistics is to maximize the likelihood. And so we take the likelihood, but we have this penalty function, which is some value, some positive number, lambda times beta, and then we maximize this. And there are various methods of maximization, which I won't go into. Well, you could, well, there are things you could try, different methods of maximizing. But the question is, why does this work to give a good estimate of beta? So first of all, the general principle that one can actually prove under certain, if you frame the mathematical background correctly, you can prove that maximum likelihood is the best way for estimating parameters. And if you take lambda large, then this will zero cause most of the coefficients of the elements of beta to go to zero, and you'll be left with just a few most important ones, and then you can gradually decrease it, lambda, and get until you're satisfied that the terms are not really relevant. And you can also then, once you have particular terms, it becomes feasible, instead of 10,000 terms, just a handful of terms, and then you can use p-values without worrying about the multiple, the effect of multiple testing. And that's where my slides end.
Thank you, David. So in essence, we have two different ways of calculating parameters. There's risk minimization that Adam presented, and then there is maximum likelihood methods that David presented. And now Rob is going to talk with us about another strategy that allows us to develop machine learning methods for survival prediction. Over to you, Rob.
Yeah, thanks. Can anyone see this?
Yes.
Okay, good, cool. So kind of building on what Adam and David have just been talking about, I'm going to talk about another adaptation of standard machine learning models to survival analysis. And in this case, I'm going to talk about how survival forests, random forests rather, have been adapted for survival analysis. So just to give a very quick recap on how they work. So they're built on decision tree models, which instead of an SVM, or which tries to make a hyperplane to separate two classes or regress to a number, decision trees fundamentally ask a series of true or false questions of the data. So this is just some synthetic numeric data I pulled up here, and they construct these true-false decision splitting decision trees which split the data at each different node into binary trees. And the you can use them for different tasks depending on what the different splitting rules, or sometimes called criterions, are. So in a regression task, you might use something like mean squared error, or in classification, you might use, there's often use information gain or Gini index or other information measures such as that. So fundamentally, you'll compute for every single feature and at different thresholds, and try to maximize whatever one of these criterion is in order to build a node. So if this first one was built, so this feature x2, they found that you get the maximum area by splitting at this value here, and that's how the tree is constructed. So random forests extend this idea by using something called bootstrap aggregation. So they will take your training data and you split it up into m different subsets of the data. So that you can then, from that, you train a model on each of the different subsets of data, and each of those will then give you a prediction, and you aggregate that to get the overall prediction across the entire training data set. And depending on the task, so if it's a classification task, you might use something like majority voting, or if it's a regression task, something like the mean of the predictions from the models, or any other amalgamation process that you can use. And then random forests take this idea, and it was found that if you use a random subset of features rather than using the same features but different data samples at each point, you can avoid correlation issues. So what that means is, let me just, if you have 4 different features, for example, features 1, 2, 3, and 4, it's better to train models on a subset of those. So features 1 and 4, and then this one's trained on 2 and 4, and this one's trained on 3 and 4. And this is important because if you do this, it reduces the variance of the final model. Because if you have a feature that's very highly correlated with a prediction, then if you have all the features in every single decision tree that you train, you're always going to get the root node will be that feature that is very highly correlated with predictions. And if you do that, then you'll get much worse performance than if you actually use a subset like this. So that's a quick recap of how random forests work. But how to extend this to survival analysis and to take account of the different features of the data, including and incorporate features like censoring, so for example. So the way we do this with random forests is you change what the splitting criterion is. And in survival analysis, they use the most common one is the log-rank test that was talked about earlier in the recap from last time. So at each root node, when you're constructing a decision tree, so if we take this example when we're training on features 1 and 4 from the previous slide, you want to find the split that will maximize the survival difference between the two different child nodes. So at each step, you will choose a feature, one of these 2 features, and a given split value, which we'll call C, and then you'll divide the data in the subset into the left or right node, depending on whether that given data point is greater than this splitting value C, and then for that you'll compute the log-rank value for that given value of X and that given value of C for these 2 child nodes, and then you'll loop through every single value of every single possible value of C and run all the different data points through that value of C until you optimize this equation where the log-rank, the value of the log-rank for the values you found, so X star and C star, is the maximum compared to the log-rank test for all values of X and C. So that's how you construct the individual decision trees, and you repeat this process at every single child node in order to maximize the survival difference between the 2 child nodes, and down to whatever your predetermined high parameter is for the depth of each tree in the ensemble. So just to recap a little bit, that's pretty much the only major difference between using random forest models for survival analysis compared to regression or classification problems. It's the splitting rule enables you to incorporate the censored data and regress to whatever prediction you're trying to make, while taking account for the fact that some of the data may be censored in that way. So the main benefit of survival random forest is that, unlike some other machine learning models that have been adapted, like survival SVMs, you can use them to predict and plot survival and hazard functions, which Wenqi will talk about a bit later. And there's also there's just other benefits of random forest, that you can use the kernel trick to change the feature representation space, but they do share the same problems as random forest, so you can't, you lose interpretability by using this ensemble method. And just very quickly as well, another version of using decision trees in an ensemble method is gradient boosting, where instead of building each individual decision tree independently, you build them sequentially, and each one learns from the previous model on what they got wrong and tries to correct those mistakes rather than learning them all independently. There's a very popular library for that, Extreme Gradient Boosting, or XGBoost, which I'm sure some of you will have used, and they've recently adapted their algorithms for survival analysis as well. It's built on top of a different model to the Cox proportional hazard model. It uses something called accelerated failure time, but fundamentally it's the exact same concept. And this has also been shown to get some good results when applied to survival analysis problems. So that's me, and I'll hand over to Fayyaz now, unless any of you have got any questions at this point.
Thank you, Rob. I'll be sharing my screen, but if there are any questions, please feel free to ask. So we've talked about 3 different ways in which we can build survival prediction models. We've talked about survival SVMs, which can either model the problem as regression, or they can model it as a ranking problem. And you can use a combination of the two. We've also talked about maximum likelihood-based estimation of survival probabilities, and the third method is to use the splitting rule of the log-rank test to build trees. But let's revert for a sec, and if someone can help me answer this question, that would be great. So if this is I want it to be an interactive session. So if someone can think of a way, what would be the simplest machine learning model that you can use for survival prediction? So remember, in survival prediction, you've got a bunch of features, you've got a time that you want to predict, which is the survival time. So what machine learning model can you use if you don't know any survival SVM or any specific models for survival prediction?
A regression model?
Yep. John, you've got a comment?
Yes, so I was just going to say you could just fit a line, yeah, that's probability.
So a naive model, which both John and Mustafa have pointed out, is simply to fit a regression or a ranking or a classification model. So let's say if I take my cases in my data in which I have survival times and stratify them into 2 groups, people with high survival and people with low survival, and I use a classification model, then that can essentially do the job. At least it would be a rudimentary way of doing the job. Another way of doing it is to fit a regression model in which we want to predict what the time is of survival for a given individual based on their features. So you can use a regression model, but these can only be used for cases for which events have taken place, for which we know what the actual survival time is. For cases in which the event has not taken place, or censored cases as they are called, we can only estimate what their current survival time is, but we won't be able to predict whether they would survive in the future or not. So that is the difficulty of using these naive approaches, but regardless, this can be a good baseline to use. So typically we are given a data set, if I can use my pen here. We're given a data set over here in which we have features, we have got times, and we've got whether there are events taking place or not. What we can do is simply try to minimize the square error between the predicted time, which is f of x, and the actual time of survival. And we can take the average of that for all the cases for which events have taken place. And then that would be a regression model. You can do the same thing for classification. You can do the same thing for ranking, as long as you restrict to cases for which events have taken place. But what information are we throwing away? We are throwing away the information about cases of that are still alive. So this model, this naive survival prediction model, would be suboptimal, as I would say, in case of censoring, because those cases that have not died yet are also informative. So and we should be able to use that information in building our model. So from a theoretical standpoint, models like machine learning models that Adam and David and Rob talked about, survival SVMs and survival trees, as well as the Cox-Net model, they are actually able to do better because they take care of censoring. So, but still, if you don't know anything else, this is a good baseline to start off with, especially if you have a large number of events. However, in typical cases, we don't have a large number of events, and we want to use something else. We want to be censoring aware. That is the essential goal of building these models. Now, we've talked about 3 different ways of building these machine learning models, right? So Rob and Adam and David have talked about these. If we put a neural network before these and we use that as a predictor, we can essentially use all of these 3 losses that we've talked about. We can use a survival SVM loss, we can use the maximum likelihood loss, or we can use the splitting based criteria that Rob presented. And we can build, or we can neurify or end-to-end learn these predictors. So if you want to neurify, for example, a survival SVM, what you would do is you would pick your favorite neural network, you would give it examples xi and xj, and your neural network with parameters theta, those are the weights, would generate predictions f of xi and f of xj for these. And then what you do is you compare these predictions using the exact same loss function that Adam presented based on the times of censoring or the time of event and the censoring variables for these 2 cases. And you compute a gradient of that and you feed back that gradient to update those weights. So for example, if you want to use the exact same formulation that Adam presented of the survival SVM, you have a loss function that is a ranking based loss function, which enables the neural network to learn to predict higher survival times for people who have actually survived longer in the training set. And then you have a regression loss function in which you're trying to predict the target variable in the training data set in cases in which for cases that have not been censored, and for cases that have been censored, you're trying to predict the lower bound on their survival times. So it's essentially the same model. As long as your loss function is differentiable, you can plug and play. And that's how all of these neural survival SVM models are built. So I won't be going through the plethora of methods that are already out there. They're essentially based on one of these 3 strategies. You take a neural network and you have a loss function that should ideally be differentiable. And if it's convex, that also helps with convergence. And then you do this exact same thing. Are there any questions on this? Any comments? So don't be scared of neurifying survival prediction. If you have a model that works for classification, you should be able to pick out that loss function, substitute a different loss function, and plug in survival data, and you now would have a model that would enable you to do survival prediction. So if you have a model for computational pathology applications that does classification, you can use essentially the same model for survival prediction as well. It's just switching out the loss function. So, but there are a few general observations that I would like to point out. The survival ranking loss that we talked about, it's guaranteed that it would give you the highest C index. I won't go into the proof, but if you're looking for a high C index, use the ranking loss. If you're trying to predict the survival times, use the survival regression loss, but it tends to overestimate survival times because it essentially is trying to predict the minimum survival time of a given individual. So it does overestimation of these. So that is where the issue is. In case of C index calculations where the ranking loss is optimal, you would need to then calibrate that output of the machine learning model so that it coincides with the survival times. It's essentially predicting a rank or whether someone survives longer than someone else, but it doesn't predict the exact survival times. And to be able to do that, you would need to recalibrate the model. That's the only additional step you need to do. But it does give you the best C index you can expect to get from any model. And you can also use a linear combination of the 2, as Adam had pointed out, but be careful. It can, instead of combining the best properties of these 2, can also combine their worst properties. That is, you would end up with overestimating the results, and you would have a poor calibration of predicting survival times. So that is the problem with that. It is also possible to use a regularized Cox regression network that David presented in the loss formulation, in which you are trying to minimize the log likelihood of survival times. So that's essentially it. If you have nonlinearities within your prediction model, you can essentially build a nonlinear estimator. So I won't go into the details of this plot, but I will draw your attention to what's over here at the bottom of the slide. you have two different models. There is a linear SVM model, and you have a neural implementation of a non-linear support vector machine, and this performs slightly better in comparison to the other one. So in certain cases, non-linear or neural implementations would be better. Okay. In the literature, as I said earlier, there are a number of methods that we can use. One of the most widely available one, and it's available in PySurvival libraries, and it's really easy to implement, is what's called multitask survival prediction model. What you essentially do is it overcomes the limitation of the previous model that I talked about of survival SVMs. It predicts, this model MTSP predicts precise survival times for a given example. But what you do is you take a time axis starting at time is equal to 0, going up till time is equal to infinity. So this should be infinity. This is a typo. And you divide this whole interval of times from 0 to infinity into these segments that are called intervals. So anything from 0 to t1 would be interval a1. And then what you do is, there's a pretty clever method. What you do is you take a single example as input, and you have a multi-headed or a multitask output prediction model that predicts whether this particular individual whose features I have input into the predictor has survived up to a certain time whose interval is indicated at a certain output. So let's say if you have a total of j intervals, you would have j outputs in your model. And if this individual survives up to time j, then what we would like to have is to produce this model to produce zeros for all outputs before that particular time s in this case, and 1 after that. So what it essentially models is that once you are dead, you stay dead. So you cannot come back alive. So that's why once you produce 1 over here, all of the corresponding values are going to be 1. And eventually at time j, which is capital J, which models time is equal to infinity, everyone dies. So that is the basic principle behind this. What you do is essentially calculate the probability or the hazard of dying at a certain time. Remember this equation of what David showed. It's quite close to that. It's not exactly that, but what we're trying to measure is the probability of an individual dying at a certain time j, and this is just a normalization constant. And what you do is then you can use this function. Once you have this, you can compute a survival function. Remember, the hazard function and the survival function were related. We discussed that in the quiz as well. And once you have this hazard function, you can estimate the survival function. And once you have that, you can build a loss function on top of that, in which you try to minimize errors of missurvival. So it's essentially the same thing, except that now you're able to predict when would this person have an event given the features. Okay, and it performs really well. First of all, are there any questions on this? So it's a pretty clever method. If you have a predictor, let's say you build a neural network and you want to transform it to survival prediction, all you need to do is to add multiple heads to it at the output, 1 for each interval of time that you want to capture. But it does require you to define those intervals of times. And in my opinion, it's a bit complex. You can directly predict the survival time rather than predicting intervals. And there is a method that can do that. But the good thing about this method is first of all, it's pretty clever and neat. It does give you certain advantages in nonlinear cases. So if you have a nonlinear survival prediction problem, you can do much better in terms of C-index values in comparison to Cox proportional hazard models. So that's the takeaway from this. There's another method called DeepSurv, which explicitly optimizes what David was presenting about log likelihood of survival probabilities. And there is a regularizer here as well. That's the only thing they add. You have a machine learning model in which you put in your features, and out comes the hazard at any given instance of dying. And then what you do is you try to estimate this, and you try to minimize this parameter with this neural network with respect to its weights by using maximum likelihood. And what you end up with is this DeepSurv model, which performs better, marginally better in certain cases. But there's a fundamental problem with this, and because it uses only cases for which events has taken place. So in my understanding, this is suboptimal if you have a lot of censored cases. So yeah, you may want to just simply use survival SVMs or neuralized versions of those there. However, the biggest problem, and if you talk about CPath literature, everything you see is essentially one of derivative of one of these three losses that I've described. So you can take up all this computational pathology literature, and I'm not going to do that right now. But if you see, you would end up seeing the same exact equations that we have described. One of those three is going to be there. Okay, so don't be intimidated by that as well. If you can write a loss function, you should be able to transform any prediction model into a survival prediction model. The biggest problem is in risk stratification and model evaluation. Let's say you got a validation set for which you know the features, you know the time, and you know the events, and you want to evaluate how good or bad your model is. So what first you want to do is to stratify these cases into different groups based on the output of your machine learning model, so that, let's say, anything that is predicted below a certain threshold that I've defined as eta goes into the low category, and everything above that goes into the high category. And once you have these two groups, then you can plot KM curves, much like what Wenqi showed in her coding. And so you have the output, and then you can plot these two curves. You can do log-rank tests to see if the machine learning model is predicting something meaningful or not. So you would get a p-value. How do we select this cutoff or eta value is interesting. Once you generate your predictions from your machine learning model, you would need to select a cutoff. So it's much like what threshold would you use for classification? When would you call something as negative, and when would you call something as positive in a classification problem? It's the same exact problem in risk stratification for survival analysis. What we want to do is to predict or to identify a threshold. We can pick different thresholds. We can use the median value, or we can use the mean value of the outputs, or we can do something called surf cut, which essentially selects the largest gap within your prediction and cuts on the basis of that. So there are different strategies. Each of them has their own limitations. But the important point is that once you select a way of making that cut, stay with it. Don't keep changing the cutoff, otherwise you would end up p-hacking, because there would exist a threshold at which two groups would be different. So that is an important point. Once you select a threshold, it's important to stay with it. The model should not be very sensitive to the choice of the threshold. So if a model is actually robust, changing the threshold by a small amount should not affect the output of your, of your log-rank test. And that is also an important point. So you can also calculate C indices that would tell you how good or bad your model is at ranking good people with good survival from people with bad survival, and you can also compute hazard ratios and everything like that. Okay, so I'll stop here to give Wenqi some time to talk about how we can actually code this up. But in the next bit or in another PaTaRI, we would be talking about some major limitations and how you can actually get away with something like this. So how can you fool the masses when reporting survival prediction results? I won't be going through all of these 15 points, but these are essentially written in a fun way, so to hack the system. So please don't do all of this, and you would do a good survival analysis project. The most important task is the estimating the quality of your prediction. So if you do a good job on doing survival analysis, you fit a machine learning model, it's also important to do a good job on ensuring that you have validated it really well, and it's really easy to mess it up. So we should be very careful in doing these survival analysis and the follow-on quality evaluation. Otherwise, we'll always keep wondering, why hasn't cancer been solved yet? Okay, so with that, I'll leave you and hand over to Wenqi. If there are any questions, feel free to ask me. Thanks, David, you're too kind. Okay, over to you, Wenqi, if there are no questions.
Okay.
Oh, there's actually a question for me, I think, from Dan. Would sequential data and making input time masking avoid what? We can carry on with the discussion in the chat, Dan. Let Wenqi carry on.
Yeah, okay, so I will show you how to use Python to do this random survival forest. and also survival SVM in the survival analysis, and how to do this performance evaluation on the simulated data. So yeah, so here we still use the same data set, which has 1,000 subjects, and each subject has 10 features, and also the time and the event information. Okay, so first in this notebook, I show you how to use random survival forest and do this performance evaluation on the data. So we first divide the data set into two parts, training and test. Yeah, and then here we need to call this, so here we call this random survival forest model, which is a function from this PySurvival package. And in this random survival forest model, there are multiple parameters that you need to set, and you can go into this PySurvival package and and then play with it. So here I use the number of trees as 200, and we fit this random survival forest model on this training data set. So then we evaluate its performance on this test data set. So here you can see on this test data set, we get this concordance index 0.79 using this concordance index function. And here we also calculate this. This Brier score. So as you can see here, we get 0.08, which is much smaller than this threshold, which is 0.20, and which is the 0.25. So which means there is very few distance between this real survival information and this predicted survival probability. Yeah, and here you can also get information like this feature importance on this fitted model. And so here you can see for each feature, there is one value, and the higher value means this feature it is more which means this feature it is more important. So you can say that X3 and X10, these two features, they have the they are the two most important features. So which means therefore this kind of feature importance information, it can help you to decide which feature you want to include in your multivariate analysis. Okay, so after we get this fitted model, we can calculate this output risk by calling this predict risk method. So we can run it on both training and also test data set. Then we can get a new feature, which is this risk score. Then, as Fayyaz said, and also we talk about it in this last notebook, we can take the mean value of this risk score in the training data set as this cutoff value. And then we can divide this training set into two parts based on this cutoff value here. Then we can fit this Kaplan-Meier model on these two groups and use log-rank test to calculate this p-value on this data set. So here we say we get p-value which is much smaller than 0.001, which means it is statistically significant to differentiate the survival probability between these two groups. And then in this test set, still we use the same cutoff value, and we divide this test set into two parts. And we need to fit this Kaplan-Meier curve on these two groups, and then do this log-rank test to calculate this p-value on this test data set. So here you can see we can still get we still can get very small p-value here. And here we call this concordance index to calculate this C index on this validation set. So here you can see we get 0.80, which shown this, and so therefore we know that this feature, which is this risk score, it is significant in both discovery and validation cohorts. Okay, and the second technique, it is survival SVM. So here we use the same data set and also the same data splitting method. So here we call this function from PySurvival package, which is kernel which is kernel SVM model. So here we fit this model on this training set. And after this training finished, we can evaluate this fitted model on this test set. So here we get concordance index on the test data set is 0.82. And still similar to random survival forest, you can call this predict risk method to generate risk score on both training and test data sets. And then you can do this later survival analysis using this new feature here. Yeah, thank you. Thank you, that's it. Is there any questions?
Saad, do you have a question? I can hear Saad, but I can't make out what he's saying. I'm sorry. Does anyone have a question? Wenqi, I have a question on evaluation here. So, have you seen any libraries that allow you to do multiple or cross-validation runs on survival analysis?
Cross-validation, yes, I think so. Yeah, maybe we can say this skillet survival. Maybe it has some relevant information, but I need to check to make sure. Yeah.
Okay. So because the question is, if you get a single p-value every time you run a cross-validation model, once you have run 5 different models, you would end up with 5 different p-values then, right?
Yeah.
So how do you go about combining those? That's one of the questions I had, and I've been looking up. There are a few answers I found, but I was wondering if there's a library that does that for you.
Okay, understand. And I think I saw it before, so maybe in this skillet survival package. Yeah, but in this PySurvival package, I didn't see it.
Okay. And have you seen any improvements in results based on SVMs when you use nonlinear or kernelized SVMs?
Yes, here. So I use here I use kernel one, and there is also one function which is linear SVM model, but I didn't try that one.
Okay.
Yeah.
Okay.
But there is one function which is also included in this PySurvival package, and the people can play with it. Yeah.
Okay. So, have you shared this notebook with the
Not yet, and I will share this link in the chat window.
Okay. Are there any other follow-up questions from this? Survival analysis is one of the fundamental problems in machine learning and statistics, especially if you want interested in identifying whether a drug is effective or whether a certain treatment is more effective than others, which is one of the fundamental problems that a lot of us are working on in one way or another. So I hope this PaTaRI session would have helped you in understanding or gaining a better understanding of machine learning principles underlying survival prediction, and these libraries or these IPython notebooks would also be helpful. Once again, I'm really grateful to all the PaTaRI survival PaTaRI volunteers who have survived so far, and I'm really grateful to them for putting in a lot of effort. We had pretty long meetings, and they have endured criticism from everyone, especially myself. So I'd just like to thank you for all your hard work on this. Your pizza is with me, and we would go for that. I promise. And thank you everyone for attending. If there are any follow-up questions, you know who to talk to for a certain thing now. So there is more support available for everyone in the group. Okay. Thank you.